Hey, Mallory. Marissa? How are you? Guys, we'll have a help session on Thursday. Help session on Thursday at 3 p.m. I'll let you know the location of that later. Okay? That'll be for the test Friday. And then on Wednesday in class, we'll treat that as a help session too. So if you have questions and you can't come to the Thursday group, then you can come on Wednesday. Okay? The Thursday is, you can receive extra credit. If you're not able to attend, but you still want to get that extra credit, just let me know. Shoot me an email. All right, let's look at some of our clicker questions. Remember, that test is going to be chapters 5, 6, and 7. So we're making it pretty far into chapter 8. We'll stop with chapter 8 today, and then we'll pick up with it again on Monday. So here, a student holds a meter stick straight out with one or more masses dangling from it. I want you to rank these in order from most to least difficult. That is, the one that has the most torque to the one that has the least torque. Oh, I'm sorry, I didn't start the base. I'll start it now. Alright, so click in your answer when you get it. If you did that before, it didn't go through. Only about 10 or 15 more seconds. Let me remind you that torque is a combination of the force and the moment arm. So torque is equal to F times R. There's actually a sine theta, but in all of these cases the angle theta is 90 degrees, so we'll just leave that off. It's equal to 1. And so what we're looking at here is the one with the biggest torque. That is the one that has the biggest force at the longest moment arm. The one with the biggest F and the biggest R. And in this case, which one is going to be the biggest? C has the biggest torque. It has the biggest force out at the longest moment arm. So that's where you're going to get the most torque. So then I know it has to be either A, C, or E. And then you can go through and compare the others and figure out which one has the next biggest torque, and then which one has the next biggest torque, and the one after that, and the one after that. We'll stop at 140, okay? 140. This is very similar to what y'all did in lab. The answer is E. We know that C is the biggest because that's the biggest mass out at the longest moment arm. In fact, if I just sort of forget about units, I can put some numbers to these. I can just say that the mass times the distance. So this would be 1,000. That's 1,000 grams times 1 meter. Now that's not really the units of torque because I'd have to convert the mass to newtons or to a force, and then or convert it to kilograms and then calculate the force. But it's okay for ranking. This would be 1,000. For B, it would be 1,000 times a half, so that would be 500. This would be 500 times 1 because it's at 1 meter. So notice that these two are equal. That can right away tell me that E is the answer. And then here I have 500 plus 250. That torque is equal to 750. I got that from saying 500 times 1 plus 500 times a half. And so my torque here is 750. No units on that because it's not really the real units of force. But it's enough for me to rank it. 1,000, 750, and then both of those have 500. This, hopefully you can recognize that these two are equal. And then once you see that, you can go through and pick out the one, well, this is the only one that has A equal B. So this is the only one that can be B. All right, let's try some others. You'll certainly see some of these ranking problems like this where you have different torques on the test. Not Friday, but on the last day of class, or the next to last day of class. You know, the semester's almost over. You'll know that, right? Like, we're really just sort of winding down now. Okay, how about this one? In this one, we have different magnitude forces. Some are at the end of the moment arm, some are at halfway, and some are actually at an angle. So what is the ranking of these torques from the largest torque to the smallest torque? Y'all know if the sine of 45, is it bigger than a half or smaller than a half? Y'all know what the sine of 45 is? It's like 0.71 or something like that. So it's bigger than a half, the sine of 45. That's right, 0.71? That is right. All right, let's stop at about 2 minutes, at 2 minutes. Okay, good. A is right. Couple things we can do here. First of all, when we recognize that the sine of 45 is bigger than a half, then we know that this torque is bigger than, say, than this torque. Because this has a torque of 2 Newton meters. 2 newtons times 1 meter. But this has a torque that's bigger than 2 Newton meters, because it would be 4 times 1 times sine of 45. So that's like 2.8 Newton meters. So this one has my biggest torque. So I can go ahead and get rid of some of these. I can get rid of this one, and I can get rid of this one, and I can get rid of this one. Now we can look at these two, A and B, and recognize that these are equal. Because I have half the force at twice the moment arm, and twice the force at half the moment arm. So these two provide the same torque. This one has a bigger force, but it's at a smaller moment arm. This one has a smaller force, but it's at a bigger moment arm. So those A and B are the same, and so I can go ahead then and finalize the answer there. Recognize that this one, C, has a torque equal to what? 2 Newton meters? It's equal to 0 Newton meters. And it's 0 because this angle is 180 degrees, and the sine of 180 is 0. Right? It's like trying to open the door by pushing on the end of the door. It doesn't work. Okay? You'll see some of these ranking problems on that test coming up in a few weeks. Okay, which of these tells you, which of these are the criteria for a rigid body being in equilibrium? Is it the net force equals 0? The net torque equals 0? Neither of those, either of those, or both of those? Good, let's stop at 45. 45. Ask your neighbor if you're uncertain about what the answer is. 45. All right, awesome. E is right. In order to have a rigid body in equilibrium, you have to have two things. You have to have the net force equals 0. That tells you that the acceleration is equal to 0. All right, and then also the net torque equal to 0, and that tells you that the angular acceleration is equal to 0. If you have something in equilibrium, you don't want it moving linearly, but you also don't want it to rotate, because both of those are important. You don't want a rotating building, nor do you want a building that's going to scoot along the ground. So both of those are important for equilibrium. We'll come back to this. Let's try this one. We're going to put Kaiza on this board somewhere where she can balance the board. You have this board that's 5 meters long. It's pivoting right here. Where can you put her in order to balance the board? Let's stop at about 125, 130. We'll go to 130. Just a few more seconds. Okay, good. D is right. There is no position on this board where she could balance it because she just doesn't have enough force nor the right moment arm. There's no place to put her. The furthest you can put her away is here, but that's not going to provide enough torque in order to balance the board. We could calculate that. We could say what is the torque provided here? I have a force downward that's 750 newtons. And so the torque, that is, what is that, clockwise or counterclockwise torque? It's clockwise, yeah. You want to think about how it's going to rotate the system. And so that's clockwise torque, and it's 750 times 4, which is, goodness, what's that, 3,000? 3,000 Newton meters. And so you want Kaiza to be able to provide the same torque on the other side. So the torque counterclockwise needs to be 3,000 in order to balance this board, and that's going to have to equal 650 newtons. That's her weight times the distance r, and then you solve that for r. 3,000 over 650, which is about 4 meters, a little more than 4 meters. But there's nowhere to the left of the pivot point, so you have to be way over here. So you can't balance that force. Okay? Let's do an example here. Remember we said that for equilibrium, that the sum of the forces has to equal to 0, and then also the sum of the torques equals to 0. So this is a very simple example of that, where I have a seesaw with 2 kids on it, and I want to know a couple of things about this. I want to know what is the normal force, and then also if this is an equilibrium, what is this distance x? This is a very, very simple statics problem. And you can see a question like this on the test. You likely will. Not on the test on Friday, mind you, but the test in a few weeks towards the end of the semester, our exam 4. So if the boy has a mass of 100 kilograms and the girl has a mass of 50 kilograms, the length x, what is that? Well, we want to calculate our torques on both sides. This is our counterclockwise torque, and this is our clockwise torque on this side, and we want to set those equal to one another. That is to say that the sum of the torques has to equal 0, and that's going to be the counterclockwise torques minus the clockwise torques. We set them negative because clockwise is negative. That's just our standard. So those two torques are going to be equal to one another. On the left-hand side, that's our counterclockwise. The mass of the girl is going to be m1 times r1, which is 2 meters. And then on the right-hand side is going to be m2 times x. Put in some values here. M1 was, that's the girl's mass, 50 kilograms, times g, times 2 meters. I'm not writing out g just because it'll cancel out in the end anyway. Equals to the mass of the boy, which was 100 kilograms, big boy, times g, times x. And then I want to solve that for x. So my g's cancel. I get 100 divided by 100, so x has to equal to 1 meter. Okay? You'll see some questions like that, just balancing the torques. I'll show you some from the old test soon. Now, in addition, if I want to know what is the normal force, here I consider the sum of the torques. But to find the normal force, I have to consider the sum of the forces, and they have to equal to 0. And so let's look at the forces that I have involved up here. I have one force that's pointing upward, that's my normal force, and then I have these 3 forces that are all pointing down. And so I'll sum up those torques. The normal force minus the weight of boy 1, girl 2, and the plank. So that's going to be equal to the force weight of the plank minus the force weight, or excuse me, the normal force minus the force weight of the plank, minus the force weight of the boy, and minus the force weight of the girl. So the normal force is equal to those weights. The normal force is equal to the plank has a weight of 100 newtons plus 500 newtons plus 1,000 newtons. This is the girl right here. This is the boy. And this is the plank. So my normal force is going to be 1,600 newtons. Okay? In statics problems, we're not going to get into this, but one of the tricks of statics problems is that, and if y'all go into engineering, I know that none of y'all are, but if you ever go into engineering, like you change your career or whatever, and you take a statics class, you'll find that you can do some other things with this that are actually kind of cool. That I can change my axis of rotation. So here it shows my axis of rotation to be right here because, you know, it's a seesaw and that's the axis about which it's rotating. But in fact, it's not rotating at all. That it's in equilibrium. So I don't have to put my axis of rotation here. I can put it over here. I can put it anywhere on this seesaw that I want. So that allows you to write more equations and be able to solve more equations and determine more unknowns. It's kind of a cool little trick for statics. But the math of it gets kind of complicated quickly, so we're not going to do it in this class. All right. Let's look at, let's do some more practice questions in the back. And then we'll look at moment of inertia. Let's try number 9 here. Number 9. I think this is exam 3, if I'm not mistaken. Is it exam 4 or 3? 4. Okay, it's exam 4. So, what is the net torque on this object? We recognize what is your axis of rotation. Figure out if there are any forces that don't provide any torque at all. And then the other torques, the other forces that provide a torque, determine are they clockwise or counterclockwise. Remembering that clockwise is negative and counterclockwise is positive. If you finish this one, go on to number 7. See number 7. All right, let's stop at, say, 225. Go on to number 7 and finish this one. 225. All right, this one looks hard right at first. We've done some like this, and in fact, in the practice problems, there are some like this as well. But once you start looking at it, you see that some of these forces just don't really matter at all. Which ones don't matter? Does this one matter? Yeah, what about this one? No, why doesn't this one matter? Why doesn't this one matter? It's at the axis of rotation, right? So it's like trying to open the door by pushing it in. You're never going to open that door because R is equal to 0, and you're not providing any torque. And then in a similar way, what about this one? Provide a torque? No, why not? Right, because there is no component that's perpendicular. It's like trying to close the door by pushing right here. That's never gonna happen because your angle there is 180 degrees, so it's providing no perpendicular component to the moment arm. So there's only one force here that's providing a torque, 20 newtons at 2 meters. So that's going to be 40 newton meters. And it is clockwise, but you know it has to be clockwise. That's the only one with 40. But it is clockwise. That is, it's causing this thing to go in this direction, about this axis. So C is the right answer. Well, let's do number 7. What is the net torque on this? Very similar question. This is 30 and 10 newtons here. All right, let's stop at 55. 55. Okay, good. D is right. In this one, you do have two torques, and you want to sum up those torques. You say that the sum of the torques is equal to your counterclockwise torques minus your clockwise torques. These over here are counterclockwise. They make this hoop turn in this direction, which is counterclockwise, and then the other causes it to turn in the clockwise direction. So this is tau clockwise. And then here I have everything's by 1 meter, so it's going to be 30 newtons times 1 meter minus 10 newtons times 1 meter, which is equal to 20 newton meters. So D is the right answer, and it is counterclockwise. Okay? I know it's counterclockwise, by the way, because this comes out positive, and so that's how I know it's counterclockwise. If it's not obvious, and sometimes it won't be obvious, because if you have 2 or 3 forces, or 3 or more forces that are causing torques, it won't be obvious, because you're not really clear on which force will dominate. All right, let's see what else we got here. Let's do number 10, and then we'll go back to moments of inertia. This is similar to the ones we did before in the concept test. I want you to rank these wrenches from greatest to least torque. Which one has the biggest torque, and which one has the smallest torque? Some of y'all look very sleepy today. Was it not a sleepy, restful weekend? Was it a sleepy weekend? Or is this just that dry? This is kind of dry, huh? Torques are kind of fun. Which is the biggest torque, or which is the smallest? Let's stop this at 105. So with these, it's best if you sort of go and identify which is the biggest torque. And so, like for example, I know that this torque is bigger than this one, right? Because it's the same force, but it's at about twice the moment time. So this is bigger, and also this one's bigger than this one. Likewise, this one is bigger than this one, because these are the same scenarios, except this force is just off at an angle. And so I'm only getting part of this force that's actually causing a torque. So already I could say C, B, and then A. And then I need to think about C and D. But C, B, and A, that would actually give me the answer to D. I could also say, well, C and D, here I have half the force at twice the moment arm, and here I have twice the force at half the moment arm. So I have the same torque for both of these. So C and D are equal, and then B and A follow after that. B is the right answer. Okay? Let's go back and look at moment of inertia for just a bit, and then I'll have y'all do something else for me. Don't forget that you have an OpenStax assignment. I wrote y'all an email last week about it. It's kind of a humdinger, okay? Like, it's long. It was, I think 25 questions, but a lot of them are easy. I don't know if any of y'all have looked at them. Have any of y'all looked at them? Do you think some of them were easy, the questions? Yeah, they were conceptual questions, some of them, and they come pretty quickly. And even the calculations aren't terribly complicated. But the more questions you get on those, the better it affects your grade. So that's why I gave you all those. And plus, it's good practice for the test. I intend to pull a number of questions from the OpenStax for the test on Friday. So it will benefit you to study them and to look over them. I'll change the numbers, of course, but you'll be able to recognize them. Okay? So that's due, I think, is it Wednesday I made it due? It is due on Wednesday at midnight. So I don't think y'all have any other tests this week, right? That's what I heard. Any other tests? Calculus. I'm sorry. On Friday? All right. Well, do well on all of them. That's really what you want to do. Okay, so far, up till now, we've sort of been translating our linear to our rotational angular quantities. That is, we let x now be theta, we let v be omega, we let a be alpha. And you probably have this on a post-it note on your bathroom mirror or whatever, right? The angular to linear quantities. We've also had our force. We're now talking about an angular force. It's not really an angular force, but we're talking about our torque, a force at a moment arm. And now we're going to come up with something for mass. And that mass is going to be called moments of inertia. So as we're transferring our linear quantities to angular quantities, this is sort of our menu that we have. X to theta, v to omega, a to alpha, f to tau, our force to torque. And then m we'll now call I, which is the moment of inertia. So for linear motion, we use the mass to describe the inertia. For angular motion, the moment of inertia as I said, we're calling I. The moment of inertia describes the inertia of the rotating body. The rotating body. The moment of inertia describes how difficult it is to change the rotational motion of the object. That's the same for our mass, right? That's what mass was. That the mass described how difficult it was to accelerate the object. That's why we had that old F equals ma bit. The bigger the mass, the bigger the bigger the force you need to accelerate it. So this is exactly the same as what we had before, as far as our idea thinking of the moments of inertia. Our moments of inertia is going to be defined in this way. It is going to be equal to the sum of m times r squared, where m is the mass of the particle, at some distance r, that distance will be r, which is the r in this equation, from the axis of rotation. Remember how we talked about how you have all sorts of different axes of rotations? And so I can have rotational motion with the same body about the same axis of rotation. So for example, like we said, I can rotate my body in all sorts of different ways. I can do it like this, like a ballerina, rotate about an axis that goes down through the middle of my head. My moment of inertia in this case is relatively small, because if you think about it, this is my axis of rotation. Look, all my mass is located just within about less than a foot of my axis of rotation. But if I want to rotate about this axis, I got all sorts of mass, big radii. I got all the way out here, my head and my arms and all this mass that extends out to these large radii. So that's why it's really difficult to rotate about this axis, because I have a very big moment of inertia. It requires a lot of torque, actually, to cause me to rotate about this axis or about this axis. But now I'm going to do it. No, I'm going to do it. But anyway, what was I saying? Oh, moment of inertia is different if I go at this axis as opposed to this axis. So if anybody ever asks you to do a cartwheel, you just say, moment of inertia is too big. Sorry. All right. So our moment of inertia is based not just on the mass, but also on the distance from the axis of rotation. The units are just come from here, kilograms and meters squared. And so, for example, if I have a very simple arrangement of particles, I just sum up the product of mr squared for each of those individual particles. And that's what this summation sign means right here. So let's consider this, for example. I want to know the moment of inertia of this. I would say I is equal to the sum of mr squared, and that's equal to 3 kilograms times 1 meter squared plus 1 kilogram times 2 meters squared plus 2 kilograms times 3 meters squared. And so my moment of inertia here is 3 plus 4 plus 18, 25 newton meters, or 25 kilogram meters squared. Okay? So that is my moment of inertia. I can also calculate, you might see a question on the test like this, where I just give you a collection of particles, and you calculate what is the moment of inertia for that collection of particles. And then we'll have some additional questions, which we'll get to next week, that deal with that. Let me show you a couple other things, and I'm going to have you do this thing for me. With calculus, we can calculate the moment of inertia for other objects. So I just think of a hoop. Say I have like a hula hoop, and I want to know the moment of inertia as it rotates about this axis. Remember, I is the sum of mr squared. And so if I break this thing down into m1, m2, m3, and on, I could do m4, m5, then it would just be m1 times r squared plus m2 times r squared plus m3 times r squared, and then on, all the way up to however many pieces I break this thing into. But this is really just a summation. I know you haven't gotten to this in calculus. I don't think you take Calc 2. But do y'all know what a summation is in calculus? What is a summation? It's an integral. So this is just an integral of the mass. I break this thing into little differential elements, and then I multiply m times r squared, and I take the integral of that as I go around that hoop. And so I then is equal to the integral of r squared times dm. You don't need to know that for the test, because we don't do calculus in this class. But it's interesting, as you see it in your calculus class, that it's really applicable in the physical world. And it is actually quite useful in the physical world to think about these 3D objects and integrate over them. Anyway, if you do that for rigid bodies, and we do this in the 200 level, where we actually derive these, but if you do that for different shapes, then you can get equations for the moments of inertia for those different shapes. I'm not going to get into this much. We'll wait until next Monday to get into this. And we'll do some practice problems with this. Okay? Let's see, right now, I want to do